G'day, in this video we're going to be looking at equipotential lines. This concept didn't fit particularly well in either of the previous calculations videos, so I thought that I'd polish off inquiry question 1 by looking at it as a concept specifically. This is going to allow us to complete our final sets of quantitative analysis of electric charges by understanding equipotential lines in a little bit more detail. So today our key learning intentions is to first unpack the polarity that we have when looking at potential for different electric fields and introduce the concept of equipotential lines. So what I wanted to unpack first is the idea that potential can be negative, that we can have a voltage which is less than 0. Generally, this negative potential forms when you are close to an electric field surrounding a negative charge, but I wanted to start to explain how and why that actually occurs. And to unpack this concept, there's two really important rules to understand to link concept to the polarity of potential. Now, the first rule here says that if you move a positive charge against field lines, you're increasing its potential energy. And if you move the particle towards the direction of the field lines, the potential energy will decrease. This rule is quite similar to what we observe in everyday life when gravitational potential energy comes into play. If we imagine picking up a ball from the ground and that the gravitational field would essentially point from the ball towards the ground, the action of lifting the ball is moving that ball against the field lines and thus increasing the potential energy of the ball. However, if you were to drop or lower the ball back towards the ground, you would be moving that ball in the same direction as the field lines, and thus the ball would be decreasing its potential energy. The interaction between a positive charge and the field lines work in exactly the same way. The second rule is that as you move a positive charge infinitely far away from a point charge that it's near, eventually the voltage becomes 0. However, technically, for a voltage to be 0, the charge would have to be infinitely away from the source of the electric field. And because a positive charge will interact differently to an electric field generated by a positive or negative source, then its potential will also act differently as well. So in a scenario where I have a positive charge, which is emitting an electric field outwards from the charge, and we place a positive point charge in that field, we can start to analyze how the potential energy in the red positive charge may change as we move it away from or towards the electric field source. According to rule 1, if we were to move the positive point charge towards the electric field source, that would mean that the potential energy would increase. And if we were to move the positive charge away from the electric field source, then the potential energy would decrease. And to apply rule 2 here, we could say at a point where D is infinite, our red positive charge is infinitely far away from the electric field source. At this point, we could say that our potential is equal to 0. Now, reflecting on the equation which relates potential energy, and charge, V equals U on Q, we can apply this concept to predict the potential of the positive charge, whether the positive charge is really close to the electric field source or is moved infinitely far away from the electric field source. So in this diagram, what we've said here is that the positive charge will increase in potential energy as it gets closer to the field source and decrease in potential energy as it moves away from the field source. If we start at our 0 point and continue to increase our potential energy as we move towards the field source, what this suggests is that voltage starts at 0 and then increases in the positive direction. So for example, the voltage could be 0 here, 1 volt, 2 volt, 3 volt, etc. What we can conclude from this is if we put a positive charge in a field which is caused by a positive charge, then the potential should be greater than 0. In other words, the potential is always positive. However, we observe the opposite if this positive charge was placed in a field which is generated by a negative charge. So here in this example, we have a negative charge, and I've drawn field lines to indicate that the field would move a proton towards the negative charge. Applying rule 1, if we were to move the proton against the direction of the electric field, which in this case would be towards the right, we would say in this scenario that potential energy is increasing, and that if we move the positive charge towards the electric field source, that this would decrease the potential energy, as we would be moving the positive charge with the direction of the field lines. Similarly though, we would have a point at an infinite distance away from the original field source, where at this point, voltage would be zero. There would be zero potential. Now, comparing this diagram to what we had in the previous scenario, the fundamental difference here is that potential energy will increase and decrease in opposite directions. Both scenarios state that the potential will become zero if we're able to get this proton infinitely far away from the original field source. However, in doing that, we'd be moving the positive charge away from the original field, moving it against the field lines, meaning here that the potential energy of the positive charge would be increasing. It would be increasing towards zero. Now, the only way to increase towards zero is to have at the beginning a negative potential energy. And reflecting on our V equals U on Q equation, if U is negative in this scenario, then V would also have to be negative. So what we can conclude here is that in fields caused by a negative charge, we can assume that the potential will always be less than zero. In other words, the potential is negative. Now, this concept can be a little bit abstract and you are playing around with lots of ups and downs and positive and negative values, but it is something that we will continue to practice in class. This now brings us to our concept of equipotentials. Essentially, you can have areas of equivalent potential that are from set distances around a single point charge. So what that kind of means is if I were to draw, say, a point charge that was positive, there would be areas around the point charge of equivalent distance. Now, obviously, I've not drawn a perfect circle around this charge, but we would say that, D equals 1 for the sake of this diagram. D equals 1 in any direction. D equals 1. We're saying at any equivalent distance around this point charge, and this would obviously be in a sphere as well, not just a two-dimensional diagram, that this line would represent a particular potential. So for example, this could be representative of, say, 2 volts of potential. As we get further away, this potential would decrease. So say if this was an equipotential line, obviously, again, I've not drawn my diagram as a perfect circle by any means, but this equipotential line could be representative of another voltage. Considering that we are moving away from the positive charge, we would expect the potential to decrease. This may be, say, 1 volt, for example. When we get into class, we're going to have a look at this FET simulation here, which does a really good job of allowing us to play around with some of these equipotential lines and even look at some more complex scenarios where we have multiple charges that are placed in an area. And what that will mean is that there are some more complex shapes which are formed for these equipotential lines. Potentially, they may look even closer to the equipotential lines that I have drawn here. Thank you very much, everyone. We'll spend our next lesson getting through some more calculations on this topic, but when we move into our next video, our focus is going to be on inquiry question 2, which begins our journey with electrodynamics and looking at electricity. We'll cover some basics as well as Ohm's law, which should be a recap from Year 9 and 10. But until then, have a good one.